Isolated conduit in air, as defined by the National Electrical Code, refers to a conduit that is not in contact with any other conductive surface. This means it's not touching things like cable trays, other conduits, or the building's structure itself. The NEC provides specific guidance on how to determine the ampacity, or current carrying capacity, of conductors installed in such conduits. Table 310.74 in the NEC is particularly relevant as it provides ampacity adjustment factors specifically for isolated conduits in air. These factors are used to adjust the base ampacity of the conductors, taking into account the number of conductors within the conduit and the conduit's diameter. Now, whether a conduit inside a building is considered isolated in air depends on its installation. If the conduit is in contact with a conductive surface, like a cable tray or a part of the building's structure, it's not considered isolated in air. If it's not touching any such surfaces, then it is considered isolated in air. When calculating the ampacity of conductors inside a building, you first need to determine if the conduit is isolated in air. If it is, you can use table 310.74 to adjust the conductor's ampacity. However, if the conduit is not isolated, then you need to use a different method, such as table 310.15b3, which is used for conduits with more than 3 current-carrying conductors. For installations involving conductors operating at 2001 volts and higher, you must pay close attention to the conductor's insulation rating. The maximum ampacity of the conductor may be limited by its insulation rating, even if it's installed in an isolated conduit in air. In these cases, it's crucial to determine the conductor's ampacity under engineering supervision. This ensures that you don't exceed the insulation rating, which could lead to premature failure or even a hazardous situation. When dealing with installations at 12,470 volts, using XLP 15 kV shielded conductors, also known as MV105, inside rigid metal conduit, the appropriate ampacity determination becomes critical. The key is to correctly apply the National Electrical Code, specifically sections 310.73 through 310.76 and related tables. First, identify whether the conduits are considered isolated in air. If they are not installed in duct banks and are indeed isolated from contact with other conductive surfaces, table 310.74 becomes relevant for ampacity adjustments. However, if the conduits are in contact with building structures or other conduits, they would not be considered isolated in air, and alternative ampacity calculation methods would be necessary. For conductors operating at these higher voltages, it's essential to consider the insulation rating of the conductor. The maximum ampacity is often limited by the insulation's temperature rating, irrespective of whether the conduit is isolated. This is particularly important for MV105 conductors. Therefore, determining the ampacity under engineering supervision is crucial. This involves considering the specific installation conditions, including ambient temperature, conductor spacing, and grouping of conductors, to ensure that the insulation rating is not exceeded. For conduits that are not isolated in air, the ampacity of the conductors must be calculated using methods applicable to non-isolated conduits. This often involves starting the ampacity based on the number of current-carrying conductors in the conduit and the ambient temperature. Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. The ambient temperature correction factors are found in Table 310.16. When dealing with high-voltage installations, it's also essential to consider the voltage drop along the conductor. Excessive voltage drop can lead to inefficient operation of equipment and potential safety hazards. Therefore, the conductor size must be selected to minimize voltage drop while staying within the allowable ampacity limits. The NEC provides guidelines for voltage drop calculations, and it's recommended to consult these guidelines to ensure that the installation meets the required performance standards. Furthermore, proper grounding and bonding are crucial for high-voltage installations to ensure safety and minimize the risk of electrical shock. The NEC provides detailed requirements for grounding and bonding, and it's essential to follow these requirements carefully. This includes ensuring that all metallic components of the electrical system, including conduits, enclosures, and equipment, are properly grounded and bonded together. In addition to the NEC requirements, it's also important to follow any applicable local codes and regulations. These codes may have additional requirements for high-voltage installations, and it's essential to be aware of these requirements to ensure compliance. Finally, it's important to document all ampacity calculations and other engineering considerations for future reference. This documentation should include the conductor size, insulation type, ampacity rating, derating factors, and any other relevant information. This documentation will be helpful for future maintenance and troubleshooting of the electrical system. Remember, when working with high-voltage installations, safety is paramount. Always follow proper safety procedures and use appropriate personal protective equipment. If you are not qualified to work on high-voltage systems, it's best to consult with a qualified electrician or engineer. Now let's delve deeper into the specific tables and sections of the NEC that are relevant to determining ampacity for isolated conduits and air, particularly for high-voltage installations. Section 310.73 through 310.76 covers specific requirements for conductors operating at voltages above 2000 volts, and these sections often refer to other tables and articles within the NEC for detailed guidance. As mentioned earlier, Table 310.74 provides ampacity adjustment factors for isolated conduits and air. This table is used to adjust the base ampacity of conductors based on factors such as the number of conductors in the conduit and the conduit's diameter. It's essential to carefully read the notes associated with this table, as they provide important clarifications and limitations on its use. For example, the notes may specify the maximum ambient temperature for which the table is applicable, or they may provide guidance on how to handle situations where the ambient temperature exceeds the table's limit. In addition to Table 310.74, Table 310.16 is also relevant for determining ampacity. This table provides the allowable ampacities of insulated conductors rated up to and including 2000 volts, and it's often used as a starting point for determining the ampacity of conductors in higher voltage installations. However, it's important to note that the ampacities in Table 310.16 are based on specific conditions, such as an ambient temperature of 30 degrees Celsius and no more than 3 current-carrying conductors in a raceway or cable. If the actual installation conditions differ from these assumptions, then the ampacity must be adjusted accordingly. For example, if the ambient temperature is higher than 30 degrees Celsius, then the ampacity must be derated using the correction factors provided in the table. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, then the ampacity must be adjusted using the adjustment factors in Table 310.15b3. It's also important to consider the conductor's insulation rating when determining ampacity. The insulation rating specifies the maximum temperature that the conductor can withstand without degrading. If the conductor's temperature exceeds its insulation rating, then the insulation may begin to break down, which can lead to premature failure or even a hazardous situation. Therefore, it's essential to ensure that the conductor's temperature remains within its insulation rating. The NEC provides guidance on how to calculate the conductor's temperature based on factors such as the conductor's ampacity, the ambient temperature, and the thermal resistance of the insulation. In some cases, it may be necessary to use larger conductors or to provide additional cooling to ensure that the conductor's temperature remains within its insulation rating. When dealing with high-voltage installations, it's also important to consider the effects of corona discharge. Corona discharge is a phenomenon that occurs when the electric field around a conductor becomes strong enough to ionize the air. This ionization can produce ozone and other corrosive gases, which can damage the conductor's insulation. To prevent corona discharge, it's important to use conductors with smooth surfaces and to avoid sharp bends or edges. It's also important to ensure that the conductors are properly shielded and grounded. In addition to the NEC requirements, it's also important to follow any applicable industry standards and best practices. For example, the Insulated Cable Engineers Association provides detailed guidelines on the selection and installation of high-voltage cables. These guidelines can be helpful in ensuring that the installation is safe and reliable. Finally, it's important to remember that determining ampacity for high-voltage installations is a complex task that requires specialized knowledge and expertise. If you are not qualified to perform these calculations, it's best to consult with a qualified electrical engineer or electrician. When considering conductors operating at 2001 volts and higher, special attention must be given to the type of insulation used. Different insulation materials have different temperature ratings which directly impact the ampacity of the conductor. For instance, MV105 rated conductors commonly used in 12,470 volt systems are designed to operate at a maximum temperature of 105 degrees Celsius. This temperature rating must be a primary consideration when determining the allowable ampacity. If the ambient temperature around the conduit is high, or if multiple conductors are bundled together, the heat generated can raise the conductor temperature above its rated limit. In such cases, the ampacity must be derated to prevent overheating and potential insulation failure. The NEC provides specific ampacity tables and adjustment factors that take these conditions into account. For example, Table 310.15b2 provides temperature correction factors for conductors installed in locations with ambient temperatures other than 30 degrees Celsius. These factors are used to reduce the allowable ampacity when the ambient temperature is higher, ensuring that the conductor temperature stays within its rating. Furthermore, Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. When multiple conductors are bundled together, the heat generated by each conductor can raise the temperature of the others, reducing their ampacity. The adjustment factors in this table account for this effect, allowing for a safe and reliable installation. In addition to these tables, it's also important to consider the specific installation conditions when determining ampacity. For example, if the conduit is installed in a location with poor ventilation, the heat generated by the conductors may not be able to dissipate effectively, leading to high conductor temperatures. In such cases, it may be necessary to use larger conductors or to provide additional ventilation to ensure that the conductor temperature stays within its rating. Another important consideration is the voltage drop along the conductor. As current flows through the conductor, it experiences a voltage drop due to the conductor's resistance. If the voltage drop is too high, it can affect the performance of the equipment being powered. The NEC provides guidelines for voltage drop calculations, and it's important to ensure that the conductor size is adequate to minimize voltage drop while staying within the allowable ampacity limits. In summary, determining the ampacity of conductors in isolated conduits in air for high-voltage systems requires a thorough understanding of the NEC, including the specific tables and adjustment factors that apply. It also requires careful consideration of the installation conditions, the conductor's insulation rating, and the potential for voltage drop. Because of the complexity involved, it's often necessary to seek the guidance of a qualified electrical engineer or electrician to ensure that the installation is safe and compliant with all applicable codes and standards. When dealing with 12,470 volt installations using XLP 15 kV shielded conductors and rigid metal conduit, the selection of the appropriate ampacity table or section in the NEC is paramount. Given the conductor voltage exceeds 2000 volts, Article 310, specifically sections 310.60 and beyond, becomes applicable. These sections provide guidelines for conductors rated 2001 volts and higher. The term isolated conduit in air implies that the conduit is not in direct contact with other conduits, building structures, or any material that could impede heat dissipation. This condition affects the ampacity as better heat dissipation allows for higher current carrying capacity. If the conduits are indeed isolated in air, Table 310.74, as previously mentioned, could be used for ampacity adjustments. However, its applicability depends on meeting all the conditions specified in the table's notes, such as ambient temperature and conductor spacing. For conduits inside a building, determining whether they are isolated in air requires a physical assessment of their installation. If the conduits are mounted on supports with adequate spacing from other surfaces, allowing for a free air circulation around them, they can be considered isolated in air. If they are tightly grouped or in contact with building materials, they are not. If the installation does not meet the criteria for isolated in air or duct bank, and no specific table directly applies, the ampacity calculation becomes more complex. In such cases, the NEC allows for ampacity determination under engineering supervision, as indicated in 310.15. This approach involves using recognized engineering practices, considering factors such as conductor insulation temperature rating, ambient temperature, grouping of conductors, and the thermal resistivity of the surrounding materials. Engineering supervision also entails documenting the calculations and assumptions made, providing a basis for future reference and ensuring compliance with safety standards. This typically involves using computer modeling or other analytical methods to accurately determine the conductor temperature under various load conditions. Furthermore, for high-voltage installations, it's essential to consider the potential for induced voltages and circulating currents in the conduit. These phenomena can affect the conductor ampacity and require careful analysis to mitigate their impact. Proper grounding and bonding of the conduit system are crucial to minimize these effects and ensure safety. In addition to the NEC requirements, it's also important to follow any applicable industry standards and best practices for high-voltage installations. These standards may provide more detailed guidance on specific aspects of the installation, such as conductor selection, installation methods, and testing procedures. In conclusion, determining the ampacity of high-voltage conductors and conduit requires a thorough understanding of the NEC, a careful assessment of the installation conditions, and the application of sound engineering judgment. When in doubt, it's always best to consult with a qualified electrical engineer or electrician to ensure that the installation is safe, reliable, and compliant with all applicable codes and standards. Remember to prioritize safety and follow all applicable regulations when working with high-voltage electrical systems.